Hey guys, Ms. Marusik here, and in this video we're going to talk about Dalton's law of partial pressure. Now, just like in our previous video with our other gas laws, Boyle's, Charles, Gay-Lussac's combined, we're going to have a formula here that we can do some calculations with to solve a particular variable. The big difference is that here with Dalton's law, we are only going to have pressures involved in our calculation. Those pressures are going to be for a mixture or a solution of two or more gases which do not react chemically. What's going to happen is that you are going to have some pressures of some individual gases, and then those gases are going to be put together in some sort of container. And our job is to figure out either that new total pressure, or if we're given the total pressure, to figure out one of the individual pressures. So to see this in action, let's go ahead and look at the picture that we see down here. We have hydrogen gas in a container, we have helium gas in a container, and we'll notice that both of these gases have their own individual pressures. These are often known as partial pressures because it's for the individual gases and not for the total that we're going to be putting together. So you'll notice here hydrogen gas is 2.4 atmospheres, helium gas is 6.0 atmospheres. And so what's going to happen is that we're going to put those two gases together into this third container. Now notice what has happened to our pressure. Our pressure is now 8.4. And if you look at your other data here, all that's happened is that we have added those two pressures together to get the total. So our formula that we use for Dalton's law is that the total pressure equals the sum of the individual partial pressures added together for however many gases we have. So here we only had two gases, but I mean, you could have 3, 4, 5, however many gases are in that mixture. Now, there's one thing we do have to be careful on when we're using this formula, and that is in order to be able to add these together to get the total, these pressures need to have all been recorded at the same volume and temperature conditions. You'll notice that each of these canisters down here is 5 liters and 20 degrees Celsius. So these pressures were recorded at those specific conditions. That is the only reason we're able to just simply add them up here. If we had pressures that were not recorded at the same temperature and volume conditions, we might have to do some calculations to get them into the same conditions. And what that would mean is that we would end up using, say, the combined law to figure out what that new pressure would be at similar conditions. We will look at one like that here in just a little bit. By the way, this is on your formula chart under the gases section, so it's on there whenever you need to use it. So with that said, let's go ahead and kind of see how the math on these problems would work. Now, often these problems are not simply just adding up the individual ones to get the total. Often what you're trying to do is actually figure out one of the individual partial pressures given what the total would be. And that's how this problem in particular works. It says here that we have a container which has oxygen, xenon, and helium in it. It has a total pressure, so I'm going to put P total here, of 972 torr. We also have pressure of helium at 6.73 psi. That's pounds per square inch. We also have pressure of oxygen at 74.1 kPa. And we want to figure out what the pressure of the xenon is in torr. Now, besides just having the same temperature and volume conditions, which we're going to assume that we have here because they didn't tell us otherwise, obviously, in order to add things up for Dalton's law, we have to be able to ensure that all of our pressures are in the same units. So just like we did before where we check our units, we want to make sure that they're all in the same unit. Well, I noticed that the total and my unknown are both in torr, but these other ones are not in torrs, and so I'm going to get them into torr. So just as a reminder, any kind of pressure conversion is always going to take one step. Whatever unit you have here, so PSI would go on the bottom, and I'm trying to get it here into torr. It's always going to take one step to make that calculation. I do need to look at my formula chart to get these equalities here. So I noticed that 14.7 PSI will be for 760 torr. And I'm going to go ahead and set up my other one here for kPa. So looking on my formula chart here, I noticed that it's 101.33 kPa for every 760 torr. So again, I'm going to go ahead and plug all that in. And let's get ourselves some numbers for those using our calculator here. So 6.73, I'm going to open parentheses, 760 divided by 14.7. That gets right around 348 torr. I'm going to do the same for my other one here, 74.1 kPa. Open 760 divided by 101.33. And that gets around 556. So again, I did go ahead and round these for sig figs. If you wanted to use all the digits, you could. But again, I usually round for sig figs. My original numbers had 3 sig figs, so 3 sig figs is probably good to show here. All right, so I've checked my units. Everything is now in torr. We're good. When I'm writing my equation, something to kind of keep in mind here, I noticed that I only had pressures, right? And so that is our key, that this would be a Dalton's law problem, is that our only pressures are mentioned anywhere in here. So I know I'm going to use that the P total equals the pressure of the helium plus the pressure of the oxygen plus the pressure of the xenon. I'm going to go ahead and give those individual pressures the label that I'm going to be using here. All right, so now we're just come to the plug and chug part of this, okay? P total was 972. Pressure of the helium was 348 once I converted it to torr. The pressure of the oxygen was 556 once I converted it to torr. And my pressure of my xenon is my unknown. So again, if it makes you feel better about algebra, you could always put X there. Now, since this is added here, obviously to get pressure by itself, I would need to subtract these over here. So a little bit different than the math we did the previous day. All right, so I'm going to have 972. I'm going to subtract over the 348. And I'm also going to subtract over the 556. And that gets us 68. So that means our pressure of our xenon is 68. If you want to include the 0.0, you could for the third sig fig. I will tell you this, because this is adding and subtracting, it does use a different rule than just using 3 sig figs. It actually uses places past the decimal as a limit. We're not going to be super picky on significant figures with this, but I thought I would just go ahead and mention it, that technically you only have to show the 68. As far as our unit, remember we converted everything into torr, so this would also be in torr here. And my law name would be Dalton. All right, so now let's see what we got on the next page. Here is another problem for you to try out. It says a mixture of 3 gases is known to have a pressure of 1.27 atmospheres. 2 of the gases have the same partial pressure, meaning we're going to have 2 things that have the same pressure, but we don't know them. And the pressure of the third gas is 650 torr. What is the individual pressure of the other 2 gases in torr. So what I would love for you to do is to take a moment, pause this video, and see if you can try out this problem. I'm going to go over it here in just a moment, but I would love to see if you can figure it out. So go ahead, pause it, try it out. All right, did you pause it? Did you try it out? Sure hope you did. All right, let's see what we had here. So first thing I did is in the dark blue color, I went ahead and wrote my data down. Told me that the P total was 1.27 atmosphere. P1 and P2, I don't know. So I put that those would be X number of torrs. So you'll see here in just a minute, I filled in X for those pressures. The third pressure is 650 torr. And since I want my answers in torr, I thought it best to convert everything into torr. So when I checked my units, I went ahead and converted atmospheres into torr here for that total pressure. And so then I just plugged everything into my formula here. My 965 was the total. P1 and P2 are unknown, but we know that they are the same value. P3 was 650. So then I did some consolidating, okay? Obviously, I want to get X by itself, so I subtracted over the 650. That left us with 315, but that was equal to X plus X, which is, of course, 2X. So to get the final answer, I would take that, divide it by 2. That gets 157.5, which you probably rounded to 158 torr, which is totally fine. Again, we're not going to be super nitpicky on sig figs. We just don't want to show a whole bunch of extra or shorten our answer by too much. So don't panic about it, but showing 158 torr would have been just fine. This law name is Dalton. All right, there's one more problem on here, and I'll be honest, this one, it's a doozy. This is probably the hardest type of Dalton problem that you would see. And you're going to see right off the bat how much data is in this problem. It says that, hey, we have a 200 milliliter sample of oxygen gas in a flask at 790 torr and 20 degrees Celsius. Okay, so there's oxygen gas. Then we have a 300 milliliter sample of xenon gas in another flask at 600 torr and 80 degrees Celsius. So we have these two gases at their own set of conditions. And we're going to take both of these gases and put them into a third container. The third container is 1.75 liters and a temperature of 25 degrees Celsius. And it wants to know what would be the total pressure in torr in the new container. Well, first thing I did, I went and wrote down all of my data. So you'll notice that I kind of organized it here a little bit. So I put all of my data for oxygen, volume of 200, pressure of 790. I went ahead and converted the temperature into Kelvin. I know it's going to need to be in that. Xenon, volume, pressure, temperature, converted it to Kelvin. My new container, which was 1.75 liters, I noticed that these other containers are in milliliters, so I went ahead and converted this into milliliters as well. My pressure is what I'm looking for here, and my temperature is 298 Kelvin once I've converted that degrees Celsius. Okay, so you're like thinking, well, what do I do next? Well, I want this pressure here in torr. And normally, if I'm putting the oxygen gas and the xenon gas together, I would just simply add up these torrs and get the total, right? But here's the problem. These were not recorded at the same temperature and volume conditions. In fact, they were both recorded at volumes and temperatures different than the container I'm even trying to put them into. So what we need to do is we need to take each of these and figure out what would be their pressure at these new set of conditions. Now let's think through that for a minute. Now let's just kind of talk about oxygen for a minute. So I'm going to cover up the xenon for a moment. Notice here I have two volumes, two temperatures, and I'm trying to figure out an unknown pressure knowing one of the pressures. Doesn't that kind of sound like some problems, say we did last time? Sure does, right? Now it doesn't involve moles, but this is a combined problem here. I want to take this data and figure out what the pressure is at the new conditions. We're also going to need to do the same thing for xenon. You're going to have to take xenon's information into the new conditions. Again, another combined formula. Once you get those two new pressures, the pressure of oxygen and the pressure of xenon, at that new set of conditions, then you're going to be able to add them together. Now, this is a great type of problem. Even though it's a little advanced for pre-AP chemistry, this is certainly worthy of being an AP level question for sure. So what I would love for y'all to take a moment to do is, now that we kind of talked through about how to do this, go ahead and see if you can try it out. I'm going to put my work and the answers up here in just a moment, but go ahead and see if you can try it. So I'll give you a moment to pause the video and try it out. All right, did you try it out? Let's see how we did. Now, I tried to organize my work a little bit here with some colors to kind of help us visualize what's happening here. So, as I said, we need to take the oxygen into the new set of conditions. So that's what I did here in blue. I converted the O2. Notice that here's my set of conditions that were listed right here. Okay, here's my new set of conditions for this container. And I went and solved pressure. This is the new pressure of oxygen in the new container. And when I solved that, I got about 91.8 torr. I then went and did the same thing for xenon. So here was xenon's initial information that I plugged in here. I then plugged in the new information here and again solved for P. This would be my new pressure of the xenon, 86.8 torr. By the way, you'll notice that I didn't write N, the number of moles. We assumed that those remained constant throughout, and so I didn't have to worry about including N in my combined formula here. All right, so now I have this new pressure of oxygen in the new container. I have this new pressure of xenon in this new container. How do we figure out the total? Well, to figure out our total pressure, we would just simply add the two of those together. And once I add the two of those together, that gets us here a total of 178.6 torr. This would involve both the combined formula, which we used kind of to convert everything, as well as Dalton's law to do this P total. So this was definitely a doozy of a question, right? This is about as hard as you would ever see. Most of the time on Dalton's law, you're going to see something a lot more simple than this. All right, I hope you're feeling good about calculating with Dalton's law. If you have any questions or need any help, please feel free to email me. Bye, guys.